Hi everyone. Today we are really delighted to have Takato Mori, a joint postdoc at PITP and YITP, to give us a talk, on this quantum discord in holography and Markov gap. So Takato finished his PhD from Silicon Valley University just recently, and he joined Perimeter recently, and let's hear what he has to.
All right. Thank you for introduction. Also, thank you for inviting me to University of Toronto. It was a beautiful city. Okay. So today I'd like to talk to you about quantum discord, which is one of the measures for quantum correlations, and also it's surprising in relation to a Markov gap. So this is based on my work in progress, which I'm writing the manuscript right now. Hopefully appears this month, but yeah, it fluctuates a bit. Okay, so I know the audience includes coming from a variety of fields, including mathematics and quantum computation and also physics. So first, I'd like to review some of the important aspects related to my research, which is holography. And then I'd like to discuss what kind of things I obtained from the analysis on quantum discord in holography. So I hope I can briefly review about holography in 20 minutes, but well, let's see. And if you have any questions, please feel free to ask me anytime. Okay, so I, as a high energy physicist, what I really want to know about is quantum gravity. And the reason we want to formulate quantum gravity is we know that in the traditional formulation of gravity, which is known as general relativity, I abbreviate as a GR here. It has been already known that GR breaks down at some point. So those points are known as a singularity. So there is a time singularity if you go back in time to the origin of our universe. And also we have some space singularity if we go to the center of the black hole. So at those kind of singularities, general relativity breaks down. So we really need quantum gravity there. And of course, there are several approaches to quantum gravity, but there is one of the promising approach to answer to the question of quantum gravity. This is known as the ADS-CFT correspondence or holographic principle. And in this framework, we can, to some sense, answer the question of what is quantum gravity and how the gravity geometry emerges. So let me briefly explain what is ADS-CFT correspondence. And this subscript D+1 and D represents the dimensions. So we first start from D+1 dimensional spacetime manifold, which we call bulk. And we particularly consider some so-called asymptotic ADS spacetime, anti-de Sitter spacetime. And this manifold has some boundary, and this is known as the asymptotic boundary. And this asymptotic boundary is a Minkowski spacetime. And this is also known as a boundary. And this has a d-dimensional spacetime. And if we consider the time slice of this cylinder, we have a boundary and a bulk. And this bulk is as I said, it's the anti-de Sitter, which is curved spacetime. So it has some non-trivial geometry. And on the other hand, we have a boundary which is one dimensional lower than the bulk. There, we consider some quantum state in a so-called conformal field theory, which is some type of quantum system with infinite Hilbert space dimensions. So this is just a two independent system. One is a geometry described by ADS spacetime, and the other is some quantum theory, which is known as a conformal field theory, living on one-dimensional lower spacetime. And the holography or ADS CFT correspondence says that actually these two gives you an equivalent description. So if you want to study quantum gravity here, we can study from the conformal field theory, which is, well, we know to some extent, because quantum gravity is something really mysterious to so far to us. But on the other hand, this conformal field theory is a kind of, well, like a many-body system, so which we know to some extent.
Maybe I should ask the naive question right at the beginning. When you say they give similar results, we're asking very different questions on the two sides, right? You're asking about the geometry of the de Sitter space, but when you talk about a quantum state in a conformal field theory, you mean the state of some other field that's living on the surface, or do you mean?
Yeah, exactly, yes. And what I mean by their equivalent is, well, okay, so I will explain shortly, actually, maybe one slide after this. So, okay, let me proceed. So this is the equivalent relation. So we under holography, what we claim here is the partition functions for the CFT living on the boundary and the gravity partition function for this bulk spacetime are actually equivalent to each other. I mean, equal to each other. And for the partition function for the CFT side, it is just usual partition function. It's just yeah, well, it's just a summation of Boltzmann factors. But on the other hand, the gravitational partition function, it's a Boltzmann factor given by this Einstein-Hilbert action, which describes Lagrangian for the gravity in general relativity, and we have to sum over all possible geometries, and that gives you a partition function for quantum gravity. Okay.
Yeah, so I'll just push one more time, if you don't mind. For the QFT, though, you must have to assume some specific Lagrangian, some specific content of field.
Right, yes.
One field, a bosonic field, doesn't matter.
Yeah, that's a good point. And actually, this is very important that I restrict to the conformal field theory. So under ADS CFT correspondence, what we usually consider is some semi-classical geometry versus some strongly coupled quantum field theory. So it's, for example, one of the famous examples is n equals 4 super Young Mills. And this is a really strongly interacting theory, and so usually we cannot follow entire like Hamiltonian dynamics generated by this Hamiltonian. But here we consider conformal field theories, which has a conformal symmetry. So actually, various kind of quantities are only determined from conformal symmetry, independent of details of this Lagrangian. So here, I don't really specify the field content, but of course, there are some of the examples of conformal field theory, like I said, for n equals 4 super Young Mills. Thank you for questions. So this is basically the relation of, under holography, but this is really mysterious summation of a geometry, and this makes the theory quantum gravity, because we are summing over all possible geometries. And of course, this is a really mysterious thing, and we don't know how to really sum over all possible geometries. But we can focus on some specific spacetime, asymptotically anti-de Sitter spacetime. Then under holography, we can say that this the partition function for CFT and allowing a little bit of fluctuations on top of CFT, then it can be described by this gravitational partition function approximated by the equation motion in general relativity, which is known as Einstein equation. So in this sense, we can compute various quantities in conformal field theory from general relativity using some geometrical quantities. So this is one figure. So this is a bulk, and this is a boundary. So this is just a Minkowski spacetime. And the conformal field theory is defined on this Minkowski spacetime. So we can compare partition function, correlation function, and also entanglement entropy, as I will describe later. And this has some geometrical interpretation in terms of this bulk spacetime given by this kind of metric. So this is a holography. And in this talk, I will consider various kind of quantum states which has this kind of holographic dual, gravity dual. So here, let me try to describe some of the famous examples of quantum states which has some gravity dual. So in the conformal field theory, we can consider vacuum, thermal state, and some energy eigenstates. And the vacuum corresponds to this kind of geometry, the pure ADS spacetime. And on the other hand, this thermal state or some energy eigenstates, which is excited states in conformal field theory, has a dual description away from this pure ADS spacetime. So since this is thermal or excited state, so it must correspond to some kind of excited geometry and thermal, like containing thermal object or some energetic object in ADS spacetime. And this is actually described as a black hole. So the vacuum state in CFT corresponds to pure ADS spacetime, and thermal state and excited states are described as black holes. So this is some of the examples of states which has a gravity dual. And well, so one may have a naive question that, okay, so there are two different states. One is thermal state, and one is the excited state. One is a mixed state, and one is a pure state. But it seems that it corresponds to the same black hole. And this is kind of mysterious. What distinguishes those two? And actually, we can distinguish from the geometrical perspective. So first of all, when we consider pure state, like this kind of excited state, it sure corresponds to the one single boundary spacetime, like this. So this is a Penrose diagram. I don't explain in detail, but basically this is a boundary, and this describes a black hole spacetime. And we only have a single boundary, which means we only have a single quantum system dual to this geometry. So this basically gives you a black hole spacetime, which is specified by temperature in terms of energy. And as here we specify energy for energy eigenstates. So this determines the black hole temperature in terms of Legendre transformation. On the other hand, I said the thermal state also corresponds to a black hole, and which means it should have some different realization compared to this pure state black hole. And this can be considered using a purification. So if you purify the thermal state, adding some auxiliary degrees of freedom, then you can write this purification so-called thermal field double state. Here we have an original quantum system and also the purifying quantum system. So there must exist two boundaries to describe two quantum systems, which means we can extend the previous spacetime, which only have a single boundary, to a second new boundary here. So this is called a maximally extended Penrose diagram. And here, this corresponds to black hole, but actually it has two boundaries. So this is called two-sided black hole. And so anyway, this sound field double state corresponds to this two-sided black hole. And if you trace out one part, it describes thermal state. And since this is specified by temperature, inverse temperature here, so this corresponds to a canonical black hole because we are specifying temperature as we specify temperature here in the thermal state. So this is the way we describe black hole in terms of quantum states under holography. And this is basically about the state versus space-time correspondence under holography. And in this talk, one very, very important notion from holography is entanglement entropy. I mean, the entanglement entropy is, of course, defined in quantum information, but under holography, we have a geometrical way to compute entanglement entropy. And this is known as the real Takanagi formula, given by this kind of thing. So this is an x direction, and this is a time slice. So we are interested in, let's say, the vacuum state at t equals 0. And let's say we are interested in entanglement entropy between one subsystem A and its complement. Then we can compute the entanglement entropy in CFT, and it turns out to be calculated from the geometrical quantity like this. So it basically tells you entanglement entropy is given by the length of a minimal curve, which is a geodesic connecting the endpoints of this subsystem. And if you divide by 4G Newton, which is just a parameter, then it gives you an entanglement entropy. So this is a formula for entanglement entropy, which has a holographic dual. And okay, so this is something for pure state. So if we have one subregion and the other subregion, if you consider two subregions together, it gives you an entire system. This is for pure state. And maybe decades ago, people ask a similar question for mixed states. So let's say we start from pure state, vacuum state, and if I trace over some of the parts, it gives you some mixed state between A and B. And for mixed state, we should also be able to discuss entanglement measure for mixed states. And the question is, what is the geometrical gravity dual for this kind of mixed state entanglement measure? And one naive generalization of holographic entanglement entropy I discussed here is so for mixed states, there are two phases. So one is, this is a, sorry, I forgot to tell you that, but so this is known as the real Takanagi surface. And the area enclosed by this real Takanagi surface and the subregion on the asymptotic boundary is called the entanglement wedge. So there are two phases. One is entanglement wedge disconnected. And the other case is, has an entanglement wedge connected between A and B. So naively, we can interpret this as has no correlation because they're kind of separated geometrically. But for this case, since the entanglement wedge is connected, it should have some correlation, non-trivial correlation between A and B. And this is argued to be quantified by so-called entanglement wedge cross-section. Entanglement wedge cross-section is a minimal surface connecting those two minimal surface separating this connected entanglement wedge. So by definition, for this case, it has no entanglement wedge cross section. So although this indeed characterizes correlation, so for this case, it has zero correlation, but for this case, it has some finite correlation, which means that the state is not a product state. But actually, it is conjectured to be due to a so-called entanglement purification, which contains a classical correlation as well. So this is actually not the entanglement correlation, entanglement measure for mixed states, but still it characterizes some of the correlation between A and B. So this is a entanglement wedge cross section and conjectured to be due to entanglement purification. So okay, so maybe it passed 20 minutes, and I hopefully you guys understand what I mean by holography here. Okay, so if you have no questions, let me proceed. Okay, so this is basically what we mean by holography. And as I said, the space connectivity corresponds to some entanglement between two subsystems. So we learned entanglement and geometry are really tied together under holographic principle. And although I won't discuss in detail, but from holography, we are really inspired to consider various kind of quantum information topics like quantum error correction, Markov recovery, random unitary dynamics. But actually, there is a quantum correlation, which is different from entanglement. And I will discuss that later in detail, but this kind of quantum correlation actually has not been actively discussed in holography. So one natural question to ask is what roles do they play, and what can we learn from this kind of quantum correlation beyond entanglement in holography? And the other motivation coming from really, quantum gravity context. So in general relativity, there is a notion of observer dependence. So in the first few slides, I said there is a singularity problem in general relativity. Some of, for example, in black hole, we have a singularity. And this singularity can be probed for some of the observer, but actually some other observers, like staying outside of black hole, cannot really see the singularity inside the black hole. So this kind of singularity breakdown of general relativity is corresponds to some choice of observers. And if I try to interpret this observer dependence in the light of holography, I mean by from the quantum mechanical perspective, then it means there are some observer can perform some certain set of measurements, and the other observer can perform a certain set of measurements. And this kind of ability of performing various kind of measurements should be related to the observer dependence here, which distinguishes whether we can see singularity or not. So to study this kind of singularity and its dependence on observer, we should really consider some quantity which is sensitive, some quantity which is sensitive to the ability of performing measurements. And to answer those questions, actually, it turns out that quantum discord is really a good quantity to look at. So to motivate you about quantum discord, let me give you simple examples. So this is a two-qubit system, and this is a classically correlated state. And this is also given by the summation of a product state. So this is classically correlated separable state which has no entanglement at all. So since this is just described as 0 and 1, so single Z basis is enough to describe this state. So this has a 1-to-1 correspondence to just a probability distribution. So this is just the same as the this is classical. This has nothing. Well, it can be described in terms of quantum states, but this is a classical state. However, we can add quantum coherence here, making this state superposition between 0 and 1s. Then this state no more described by single Z basis, but we need to consider this kind of superposition. So, but on the other hand, we still have this state is still separable because it's a summation of a product states. So this has no entanglement, but they are not classically correlated due to this quantum coherence. So the natural question to ask is, how can we quantify such a kind of quantum correlation even when there is no entanglement at all? So to answer this question, what we can do is define so-called quantum discord. And maybe I forgot to emphasize here, but for classically correlated state like this, the mutual information, quantum mutual information equals to classical mutual information. But on the other hand, for this state, quantum mutual information is not equals to the classical mutual information. So the naive intuition is the difference between quantum mutual information and classical mutual information quantifies this kind of quantum correlation. So the quantum discord, measurement-dependent quantum discord is defined as a difference between the mutual information, two mutual informations. And this J pi is defined like this one. So this basically tells you the difference between entanglement entropy before and after the measurement. This pi means the measurement on subsystem B. So we have two subsystems A and B, and we consider measurement on B with a particular basis, or more specifically, more precisely speaking, we consider some P of M on B. Then we can define measurement-dependent quantum discord based on the measurement on the subsystem B. So this basically tells you locally inaccessible information from the measurement on subsystem B. And if I try to maximize the, sorry, I forgot to tell you, but this J pi is called the Ozawa-Grombold information gain. So this is basically tells you how much information can you obtain through the measurement. And if I try to maximize the measurement, maximize this information gain over all possible PLVMs on the B, on the subsystem B, then it defines a quantum discord independent of the measurement. So this gives you the quantum correlation between A and B with respect to the measurement on B. Okay, so far so good? Great. So, let me give you a explicit example so that you can know, indeed, this quantum discord quantifies quantum correlation. So let's consider this kind of probabilistic mixture between classically correlated state versus maximally entangled state. So when the P equals 0, this state is classically correlated, has 0 entanglement and 0 quantum correlation. And for P equals 1, this is a maximally entangled state. So it has no classical correlation. It is maximally quantumly correlated. So this is a quantum discord after optimization. This Z actually, Z basis measurement maximizes this quantum discord. Sorry, minimize the quantum discord. So for P equals 0, this is 0 as I expected. And this becomes maximum for P equals 1 as I expected. And this actually equals to the value of entanglement entropy. So this interpolates, this indeed represents quantum correlation. And if you consider some random measurement, like if I just consider projecting measurement onto the plus states and minus states. So if I consider the X basis measurement, then actually it gives you very large quantum discord and it has very low information gain. So the measurement cannot be randomly chosen. We need to really optimize the quantum discord in order to evaluate the true quantum correlation between A and B. So this is the end of introduction to quantum discord. And from now on, using the technique of a holography, I'd like to evaluate the quantum discord in holography. But there are various kind of technical difficulties, and hopefully I can show you why there is a kind of technical difficulties and how I can overcome these. First of all, quantum field theory is very hard. It's the dimension is infinite. And as I said in quantum discord, we need to optimize over all possible POVMs. And for infinite dimensional Hilbert space. And this is really hard. And actually, it's known that quantum discord is, the computation is known to be an NP complete. So you can easily imagine this is almost not doable at all. So something we can try as a first step is try to see if there is any non-trivial bounds on the quantum discord. So toward that goal, I'd like to utilize holographic duality, especially focusing on ADS3 CFT2 correspondence, which means that bulk is three-dimensional spacetime. So if I consider the time slice, it is given by two-dimensional space like this, and the boundary is 1 plus 1 dimensional spacetime, which means it's like a circle surrounding the cylinder. So okay, so this is the entanglement entropy, geometrical realization entanglement entropy, and this is a geometrical realization of entanglement and purification. Using these notions, actually, we can obtain an upper bound on the quantum discord in holography. So first of all, there is some kind of monogamy relation originated from so-called Kawashii-Winter relation. I won't give you the proof, but please trust me that quantum discord is given by, can be written in terms of entanglement formation, which is defined somewhere around here, yes. So the quantum discord minus conditional entropy, which is determined like this, is given by entanglement formation. That's something proven. And this C is a purifier for the mixed state rho AB. And furthermore, entanglement formation is known to be bounded from above by entanglement purification. And remember, I said entanglement purification has a gravity dual, geometrical realization in terms of entanglement wedge cross-section. So now we can give you the upper bound on the quantum discord like this, which I call wedge discord. So this upper bound on quantum discord, which I call wedge discord, can be written in terms of the entanglement entropies and also the entanglement wedge cross-section, which both have a geometrical realization. So this gives you an upper bound in holography. And something really good about this quantity is, well, this has a manifest realization in terms of geometrical quantities. And also it involves no optimization. So we can just compute easily. And we're going to compute that, and we're going to show you the result for this computation later. But let me try to give you the lower bound on quantum discord as well. And actually, it turns out the lower bound also equals to this wedge discord. So, as I said, the original definition of quantum discord is like this: mutual information minus the maximized information gain. And the information gain is given by this one. So we need to maximize this quantity. Sorry, since there is a minus sign, so we need to minimize this quantity. And so usually this optimization is really hard. But something you can make a guess. So since J represents information gain, so it means maximize the measurement which maximize the information gain should be something really a very complex measurement. And for black holes, actually, we have a kind of intuition. So for black hole, what we want to know is, for black hole, we can make a various measurement. But for example, if I try to just measure the energy or temperature of the black hole, it is just determined from the classical geometry. So this is something we can easily know. But something something it is very difficult to know through the measurement is the information about black hole microstates. So the idea is as follows. So even when we have a black hole spacetime, there could be various kind of quantum states realizing similar kind of geometries. One of the examples I gave before is thermal state versus energy eigenstates. They are different states, but give you the same semi-classical geometry. So some measurements which could have very large information gain would be something try to distinguish the black hole microstates, which gives the same geometry. So, something we can consider as a candidate for this measurement is a projecting measurement distinguishing black hole microstates. And so this is a measurement. So this is a measurement try to consider pure state of this energy eigenstates and try to discriminate all the black hole microstates through the measurement. And actually, this can be evaluated once you are considering so-called saddle point approximation, which is valid if you take a semi-classical limit, which means where the general relativity is valid. And we can show that this actually can be given by the single entanglement entropy, but whose state is a kind of representative state, which dominates this summation. And this energy is actually given by, so this is a sum field double state case. And let's see, so originally we start from a sum field double state, so which has some fixed temperature. And this E star is a state with a certain energy. And this energy turns out to be an energy obtained from the temperature given from sum field double state through the Legendre transformation. So actually, we know what's the energy here. So after all we need to compute is entanglement entropy for this kind of pure state. But actually, there is one more subtlety here. As I said, we need to consider maximizing information gain, which means minimizing this quantity, which means minimizing this entanglement entropy. And actually specifying the energy, it's not really sufficient to find a to complete this minimization. This is because even if we specify the energy, I won't go in details, but it is known that the geometry describing this certain energy state could have some singular behavior around this horizon. So this horizon might give you some various kind of contributions to entanglement entropy. So this is actually not different from the state to state. However, the minimization is actually easy. Even if we have a various kind of, even if we have a variety of possibilities that we have some kind of contribution to entanglement entropy from the horizon, but minimization can be achieved by neglecting those kind of contributions, because these contributions just gives you contribution to in the form of entanglement entropy. And you know entanglement entropy is non-negative. So the minimization can be achieved by just set those contributions to 0. However, it is not guaranteed that this kind of state really dominates the summation here. So which means we only get the lower bound on the quantum discord. And this quantity, for example, this is one of the case. So before the measurement, let's say entanglement entropy is computed like this. But after the measurement, this can attach to this horizon. So this no longer computes the entanglement entropy, but this is smaller than this one. So this is one of the case computing this one. And it turns out to be this actually is equivalent to the entangled wedge cross-section between A and its purifier C. So after all, what I would like to emphasize here is the upper bound is, as I said, it's given by the wedge discord. And the lower bound, it can be shown here, lower bound is also given by the wedge discord. Since the upper bound and lower bound here coincide each other, so which means the discord is given by the wedge discord. And actually, I'm not sure whether what's the implication here, but the this d equals dw implies that the entanglement purification actually equals to entanglement formation to the leading order. And so I guess there are some quantum information theorists here. So hopefully, if anybody knows what's the implication here, I'd like to hear from you. Anyway, so there is anyway, the quantum discord in holography is given by this wedge discord. Okay, so okay, I still have some time. Let me proceed to describe what kind of properties and behavior this wedge discord, quantum discord in holography have. So there are various kind of properties. But first of all, let me describe that there are some satisfactory properties where the quantum discord had. So for example, if I consider tripartite entangled state, so-called GHZ state, then if we consider any two parties from these three parties, the quantum discord vanishes. So this is kind of sensitive to some class of tripartite entanglement. And also, if the quantum discord is 0, which means quantum correlation is 0. So which means the state is separable. But actually, converse is not always true. Even if the state is separable, has no entanglement, discord can be non-zero, as I said in the beginning. And also, the discord is bounded. This is non-negative and also bounded from above by mutual information. And this is really satisfactory because usually we expect that quantum correlation is bounded from above by total correlation, which is characterized by mutual information. And finally, when the state is pure, this discord equals the entanglement entropy. That's also a good property because it represents a quantum correlation. And finally, for holographic system, actually, I can show the wedge discord has more desirable properties. For under holography, actually, one can show that the zero discord means the state is separable. It's if and only if relation. So actually, this discord can be also useful as an entanglement witness. And also one can show that there is no GHZ entanglement in holography. That's one application of this quantum discord. And there are several additional properties, like this is non-monogamous, and which is actually equivalent to the non-negativity of this Markov gap, which I will explain this Markov gap later. And also this can be shown to be greater than or equal to 1/2 of mutual information. Okay, so there are several properties. Let me give you more concrete examples. So here I consider two setups. One is Stanfield double state. So we consider measuring one side of the two-sided black hole, and we consider subsystem A as a length L subsystem on the other side. And also we consider some two intervals, A and B, whose lengths are equal, given by B minus A. And this is basically the figure. So let me briefly explain some interesting feature. So this is the horizontal axis is the size of the subregion A. And this dashed line, like here, this shows a mutual information. And the quantum discord, sorry, it's really difficult to see, but the quantum discord goes something like this. So this is always bounded by this mutual information. And also the entangled wedge cross-section, I said this quantifies some kind of quantum correlation. Actually, this is not really a good correlation measure because it can exceed mutual information. So there is some kind of overcounting. But there is no this kind of discontinuity for quantum discord, and it eventually saturates at some point. This is entanglement entropy. And also this is always bounded from below by 1/2 of mutual information. And this is for the vacuum interval case. Basically, it has a similar behavior. So I want to explain further. Okay, so these are some computations for quantum discord in holography. So this can be the quantum discord in holography can be described using a linear combination of some geometric quantities, and which involves no optimization. And I show that the lower bound and upper bound matches together. So there is no actually optimization really needed. And here, from now on, in the beginning, I said there is a quantum correlation which is different from entanglement. So something I'm interested in here is there any non-entanglement quantum correlation in holography? And also, this kind of definition of this kind of expression of quantum discord in holography might tell you something beyond the holographic regime. And so here I'd like to discuss a 2-qubit mixer state and show you some relation to a so-called Markov gap. Okay, so what is the non-entanglement quantum correlation? So I said that the quantum discord quantity has quantum correlations in general. So in order to define non-entanglement quantum correlation, one must subtract entanglement from the quantum discord. And so far, please tell me if there is any better measures for quantum entanglement. But so far, I know that so-called squash entanglement, defined like this, gives you the best entanglement measure. So here, I'd like to consider this quantity, the wedge discord, quantum discord in holography minus squash entanglement. And it has been discussed in various papers that squash entanglement in holography is given by 1/2 of mutual information. So we can consider the quantum discord, which is given in terms of entanglement entropies and quantum wedge, entangled wedge cross section minus 1/2 of mutual information. And this turns out to equal to 1/2 of a so-called Markov gap. And this Markov gap is defined as a reflected entropy minus mutual information. And this reflected entropy is, sorry, I forgot to put the definition, but the reflected entropy is basically the entanglement entropy for canonically purified state. So like if I have a quantum state rho AB, you can double the Hilbert space just using a Choi-Jamel-Minkowski isomorphism and to consider some purified state. And for that state, we consider bipartition, and that defines a reflected entropy. So I don't discuss this detail here, but it has been known that this Markov gap is related to the fidelity of optimal Markov recovery process. So this is something to do with the fidelity of recovery process. And also it's related to a tripartite entanglement. But anyway, something I'd like to emphasize here is there is it seems there is some relation between the non-entanglement quantum correlation and this kind of Markov gap, which quantifies fidelity of optimal Markov recovery process. But actually, the parties are different. This is for A and B, and this is for A and C, which is a purifier. And maybe I can explain this a little bit. So in holography, it has been discussed that this Markov gap is lower bounded from these geometric quantities. So for this A and C, this gives you an entangled wedge cross section. The length gives you entangled wedge cross section. But here, this number of cross section boundaries means the number of intersections between this one and this edge. So this means here in this case we have 2. So this is 2. So indeed, this is a geometrical quantity.
What's C
C. Oh, sorry, I forgot to explain that. But the C is basically the central charge of the CFT. So it is a kind of parameter.
Rho ABC, you're considering a pure state.
Rho ABC is a pure state. Yes, C is a pure state. Yeah. So the is it possible to write somewhere? Wait, let's see if I have it. Yeah, but I think I have some slide. Yeah. So so rho if I consider rho AB, and we can consider canonical purification by doubling the Hilbert space. So the double Hilbert space is described by A star, B star. And we consider rho A, B, B star, this kind of three-party mixed state. And on the other hand, we try to estimate, try to recover this rho A, B, B star just from rho A, B. This is a recovery map. And we try to maximize the fidelity between those two. And this fidelity is basically bounded from above by this so-called Markov gap. So this is a kind representing kind of type of fidelity for type of recovery process on the canonical purified state. Yeah, I know it's not so
So
intuitive.
no ABB star, I just consider this as like you do the canonical purification of ABB and
Yeah.
trace out a star.
Yeah, exactly. Yes. I'm not sure why this turns out to be related to the non-entanglement quantum correlation. So yeah, that's something I don't really understand, and I'd like to understand further. Okay. So here I basically computed this right-hand side versus this quantity here. And this is indeed lower bounded. But actually for both cases, we can show that this is not really saturated. This lower bound is not achieved in these cases. And so far, I've discussed only in the holographic systems. And I know that holographic systems are far from the quantum systems we usually see, like free bosons or Gaussian states or some few qubit systems. So is there anything we can learn from this observation applicable for such kind of non-holographic systems? So toward that goal, we need to extend our proposal, that is wedge discord, to some quantity which can be computed for this kind of non-holographic systems. And there is a, sorry, I forgot the 1/2, but there is a proposal in time wedge cross section equals the 1/2 of reflected entropy. Now we have a definition. So this rho 1/2 is a canonical purification of this rho AB. And this reflected entropy is von Neumann entropy for A prime. And using this reflected entropy, I can define the wedge disk, the so-called reflected discord like this. And for holographic system, this equals the wedge discord I discussed before. And I computed this for this kind of family of states. So this has a parameter theta, so which superposes the 0 and 1s. And here you can see that they are separable. So it has no entanglement, but it has some kind of quantum discord. So if I take a theta equals pi over 4, this is something we discussed before. This has some discord, positive discord, but for theta equals 0, this is just product state. So it has no entanglement, no discord, no classical correlation. And for theta equals pi over 2, this has a correlation, classical correlation, but they have no quantum correlation. So this is one good playground to see what is a quantum discord here. And also, let me emphasize here, since this is manifested separable, so we are sure that squash entanglement is 0. So the quantum discord here equals to the non-entanglement quantum correlation. And now I did a numerical, I did an optimization. Optimization parameter is found to be something like this. And so discord is something like this. And sorry, please ignore this one. And 1/2 of Markov gap is like this one. And it turns out to be that the quantum discord here equals to the Markov gap. So this is different from the something we learned from holography. But again, as we see in holography, there seems to be some non-trivial relation between the quantum discord or non-entanglement quantum correlation and a Markov gap between the subsystem A and its purifier. So this is something I want to understand more, but so far I don't have a explanation from quantum information. This is a kind of surprising result. So this is before summarizing this, since I have just 1 minute, so let me try to describe what are possible future works. So quantum discourse has some interpretation as a locally inaccessible information. So like, for example, if I consider EPR state, this EPR correlation is inaccessible locally, because locally any measurements perceives this as just a maximally mixed state. And similar thing happened actually in this black hole spacetime. So the black hole spacetime, two-sided black hole is described as Tanfield double state. It is kind of like an EPR state. And this is actually not traversable. If I try to send signal from one side, it can't reach the other side, but it just reaches to the singularity, just goes away. And this non-traversability might be related to this, to the fact that this state is locally inaccessible at all. So I guess the quantum discourse might represent some kind of non-traversability of this black hole spacetime. And for the other work, so the quantum discourse basically defines quantum correlation with respect to the measurement on the subsystem B. So which means the exchanging A and B gives you a different quantum discourse. There is asymmetry. And there is also a kind of asymmetry in the black hole case. So if I consider correlation between the outside of the black hole and the inside of the black hole, throw the information from outside to the inside, it's easy. Just throw the diary into the black hole. That can be easily done. But try to decode the information of a diary from outside is really hard. We need really an exponentially complex recovery map to decode the information. So I guess this kind of asymmetry of quantum discourse might be useful to quantify this kind of one-wayness of the recovery of information. Okay, so this is a summary of my talk. Here we consider quantum correlation beyond the entanglement, and this can be characterized by quantum discourse. And in holography, I show that this is described by these geometrical quantities. And for non-entanglement quantum correlation, I show that this is given by the 1/2 of Markov gap, which is related to some recovery process, a fidelity or recovery process. So there might be some interesting relation between non-entanglement quantum correlation and this Markov recovery process. And even beyond the holographic system, like 2-qubit systems, there could be some kind of this kind of relation connecting quantum discourse or non-entanglement quantum correlation to this Markov gap. Okay, so that's the end of my talk. Thank you for listening.